Okay, YouTube, in this video I just want to briefly explain how we can distinguish in general form, not necessarily in standard form, but in general form, what type of a conic something is just by relating the ax squared and the cy squared term here. Essentially a and c are going to be the two values that we relate all of the time. But one thing that I do want to point out is this: as you deal with things in general form, a lot of the times we convert them into standard form, which requires that we complete the square. Okay, and when we do complete the square, the values of a and c here, the fact is, if they're being added together or subtracted is one thing that is kind of really important, but also what their sizes, their magnitude is with respect to each other. And we'll take a look at an example of why it happens the way it does. But start with some pretty basic things. We say that if a and c here are at least the coefficients of your squared terms, okay, if they're ever the exact same thing, then I can guarantee you that you are dealing with a circle, okay? So that being said, the fact that they're exactly the same, you're dealing with a circle. What if I said that, a times c is equal to 0? That would mean that one of these values here, one of these coefficients is 0 itself. So I want you to ask yourself, what's true about a term if its coefficient is 0? And I suppose the answer would be that the term would not exist. So let's imagine this hypothetical situation, but let's say that c is the value that is equal to 0 and it does not exist. So then a times c would be equal to 0. But we'd say, why is this a parabola? Well, it's a parabola because I only have an x term being squared and the y term is not also being squared. Remember, when you square both terms, you're either dealing with a circle, ellipse, or hyperbola, but when you're only squaring one of these, then that's when you're dealing with a parabola. So let's say, for instance, that the a value is 0, then I would say, well, then I have a parabola that's side-to-side opening, since our y squared term exists, but our ax squared term does not. Okay, so if a parabola, then we'd say that it only has one thing that's being squared, essentially. You don't have to run this check on it, but this is the check. So now these next two, we say if a times c equals positive, and and we say bigger than 0 is a fancy way of saying positive, as opposed to a times c equals negative, then basically what we're saying is that a times c are either both positive or both negative. Now, we're going to assume if they were both negative, we would make them both positive again anyways, but essentially what we're saying is between the two squared terms there is a sum. There's a plus sign. So what we're saying here is this: if that's a plus sign, then you're dealing with an ellipse, but if it's a minus sign, if there's a negative sign, then they have different signs, then their product would be negative. And so therefore we would say them having different signs, we could say that it'd be a difference between those two things. So whenever you have a difference between your x squared and your y squared terms, then you're dealing with a hyperbola. So when I said, let's confront a situation down here, we talk about why these coefficients work the way they do, let's go ahead and confront this first issue. We say, do any of these down here classify themselves as like a circle? And so when we say a and c, we're saying the coefficients of the squared terms. And so I'd say, well, this first one here, 4 is the coefficient of the x squared term. That's like our a. I noticed that there is no y squared term here. So since there's only an x squared and no y squared, we would say that a times c would be 4 times 0, or 0. And we're dealing with then a parabola. But essentially, I could have told you that this was a parabola just by telling you instantly that, look, you only have an x squared term and not a y squared term. Looking at this next general form equation, you notice that you have a 4 for a coefficient of your x squared term and a negative 1 for a coefficient of your y squared term. So 4 times negative 1 is obviously negative, so this is going to be a hyperbola. But this is also a hyperbola because whenever you have a difference between your two squared terms, then you're dealing with a hyperbola. What if you have a sum of your two squared terms? Like, what if we have a sum like on this next one? We say a times c. In this case, 2 times 4 would be positive, okay? But that would mean that it's an ellipse. But it also means an ellipse because these two things are being added together. Your squared terms are being added together. You're dealing with an ellipse. And what if you had an ellipse where a times c are not only positive, but they're exactly the same thing? Then this is when you're dealing with a circle, and that's that top option that you see up here where a times c are equal. So let's talk about really quickly here why that works out the way it does. And we'll look at this last example. I'm going to complete the square on this last example. So 2x squared minus 8x, and then we'd say plus 2y squared plus 12y, and I'm going to boot that constant over to the other side, negative 2. And so we're going to do a fair amount of factoring here. We say 2x squared minus 4x plus what we desire to have this here. We're going to factor out a 2 over here also. We get a y squared plus 6y plus blank is equal to negative 2, and we're going to put in half of negative 4 squared is 4, and then half of 6 squared is 9, and we're going to add 2 times 4 and 2 times 9 to the right side, so 2 times 4 is 8, and 2 times 9 is 18, and then we get down to this. We say x minus 2 squared is 2y plus 3 squared, and the right side looks like we get 6 plus 18 is 24. But here's the point where I'm just going to stop, and I'm going to tell you that we're not done putting this in standard form, but our very next step is to like divide everything by 24. And so the whole idea here is this. First things first, because this is a sum, because it's a sum, you have to be dealing with an ellipse or a circle, whereas if this was a difference, you'd have a hyperbola. So number one is sum or difference. I mean, like that's going to give you a big indication of what you're dealing with. You notice that I have an x squared and a y squared term, so this can't be a parabola. That only has one term being squared. So I already know this is a circle and an ellipse, and if I said, well, why is this a circle? You're noticing here, hopefully, that these two values are the same. And where did I get 2 and 2? Hey, you guys, those were your a and c values. Those were the coefficients of your squared terms that you had to factor out. And if you're about to divide each of those or reduce them with the exact same factor down here, what you're going to get is a situation where the bottom of these two fractions are identical. So not only do you have an ellipse, you have a very special ellipse, which would have to be a circle, because wherever the center is, you would go just as far left and right as you would up and down, and you would get this thing that casts a circle. So that is why when a and c are equal, you have a circle, whereas a and c, it's still a sum, but they're not equal, then you're dealing with an ellipse. But this is a more general way to, no pun intended, find what type of an ellipse, what type of a conic section something is by looking at its general form equation. Cheers.